Okay, since that now we understand what is algebra and the intuition of it and the requirement, the concept, everything that was bothering you since you started learning about algebra, we discussed in the previous two videos. So if you haven't watched them, go watch them now. But if you have watched them, then you wouldn't be actually be annoyed with algebra. You would actually be appreciating it, and you wouldn't be saying stuff like, "Oh, why am I adding x and y's and what is this nonsense alphabetic stuff in mathematics?" So you wouldn't be saying stuff like that. You would actually be appreciating that. So this video is very crucial because it helps you understand the dynamics of algebra, how it works, how everything in algebra works around, and how do we solve equations. So I always like to draw a seesaw in order to represent an equation because it is pretty useful to draw one because it represents an equation, right? So this pivot point actually represents the sign of equality, and whatever you have on this side is actually the left-hand side of the equation. Whatever you got on this side is actually the right-hand side of the equation. For example, I have uh, a box here, or I could just draw mini boxes, small ones, one, two, three boxes, right? Or you could just say four boxes. And I can draw on the other side a couple of balls, right? So since the seesaw is in balance, you would assume that the mass of the four small boxes is equal to the mass of the two balls here, right? So it could be because of these are made of different materials or whatever the reason, but since they're inequality, that means they're same, right? The masses on the both sides are same. So if you, for example, you want to add two more boxes here. So my question is, how many balls would you be adding on this side of the seesaw in order to keep in balance? You would say, yeah, I'm very intelligent human being, so I know I just need to add one more ball. But how did you figure it out? Since the problem was pretty simple, then you actually figured it out pretty easily. But what if this problem could have been really complex and you actually didn't know how to actually deal with it? So we need to standardize a systematic way in order to solve problem like this. So at first there were four boxes here. We are going to represent boxes using an alphabet like X, and we are going to represent balls using uh, you know an alphabet like Y, right? And now we can construct an equation on the basis of the information that was given to us previously, which was this, that 4x, like four boxes, were equal to 2y or two balls, right? Previously it was this. And with that, you can actually find out the value of one of the box, the mass of one of the box, right? X is equal to, you just need to get rid of let me actually do it this way. I need to erase whatever I just drew afterwards. We will consider the case we were discussing before, right? So how do we find the mass of one box, right? If we are able to find the mass of one box, then everything is easy for us to calculate. So what we can do here is that we can remove each like a ball at a time and see what does uh, what does the equivalent mass of the boxes are, for example. So what I'm trying to say here is that we could just remove one of the balls here. I remove one of the balls, and I would see that consequently I would have to remove two of the boxes on this side. So I come to know that okay, the value of one ball is equal to two. Value of one ball or one y, which is y, is equal to 2x. We know that value of one ball is equal to 2x, right? So the other time we had like one, two, three, four, five, six boxes. So we were supposed to find how many balls we would have. So in that case, we actually have 6x, six boxes, right? And since we multiplied 2x with 3, we multiplied 2x with 3, right? We multiplied it with 3. We also need to multiply y with 3, right? So that would become 3y. So we need to draw three balls here, right? A total of three balls. So three balls would be equivalent to six boxes. The point that I want to make from this example is that in a mathematical equation or a seesaw or whatever, whatever you do on the one side of equation, you must do it on the other side of equation. Like you just multiplied 3 on this side of the equation, you must multiply 3 on this side of equation as well. For example, you remove half of the boxes from this side. You remove half of the boxes from this side like this, and you must remove half of the balls from this side as well. So you're left with 1.5 ball, right? So this is 1.5 ball. So let's see if this works in our equation scenario or not. So we are dividing both sides with 2, right? And we get 3 by 2y is equal to 3x, right? We can see that y are the balls in 3 by 2 or 1.5, balls are equal to 3 boxes. We can see there are 3 boxes here. So we get a general principle. Whatever you do on one side of equation is something that you must do on other side of equation as well. However, you cannot just be doing the same stuff in the case of addition and subtraction. Remember that. Because if you, for example, add one box here, does that mean that you need to add one ball here? No, you don't do that because all the type of material, the objects on both sides are of different type. For example, if you had a seesaw in which on both sides you had boxes, right? Then you can see that on both sides of the equation, the objects are same. The kind of objects is same. Then if you add one box on this side, that must mean that you add another box on the other side. So in case of addition and subtraction, you need to have same variable on both sides of equations, and in order to multiplication and division, in case of that, uh, you can have either type of or any type of material on the different side of seesaws. For example, 2x is equal to, or 2x plus 5, 2x plus 5 is equal to 10. If you want to add 3 here, you must add a 3 here in order to keep it in balance. If you're dividing 2 from everything here, you must divide 2 from everything here. So this is what I'm trying to say. This is the general principle that we follow in algebra. Whatever you do on one side of equation is something you must do on the other side of equation as well.